looking at notes KK-1, rationals, day 1. So when I say rationals, I mean rational functions. So you may hear that word or those two words, and you may remember back to Algebra 2 when we dealt with the rational parent function. So the rational parent function looks as follows: two curves, one in the first quadrant, one in the third. Remember that it contains two asymptotes. It has a vertical asymptote and a horizontal asymptote. The vertical asymptote on the y-axis with the horizontal asymptote on the x-axis. Remember that those asymptotes act like magnets and they pull the curves close to them, as close as they can get without crossing or touching. So that's your rational parent function from Algebra 2. This is an example of the rational parent function reflected. Okay, so you'll notice the curves are in the opposite quadrants from before. You may or may not have seen something like this in Algebra 2, but this is another example of a rational function. And right here, because this is going to help us when we start graphing today, when we're dealing with these rational functions, I just want to refresh that this would not be a function. So if you're trying to graph and you're stuck and you think that something might look like this, you would say to yourself, no way, can't work, it's not a function because this doesn't pass the vertical line test. Okay, so just be aware the curves can be in various quadrants, but you'll never have a situation where your graph doesn't pass the vertical line test. All right, so moving on, holes. Holes in the graph are where factors cancel. So today when we're working with our equations, our functions, you might have situations where a factor from the numerator cancels with the factor in the denominator, okay? I don't like the word cancel, you know that, but simplifies out of the equation, okay? So when that happens, you get a hole, and we're going to talk about that and look at an example. Intercepts on the graph could be x-intercepts, y-intercepts. They're always thought of as ordered pairs. Those are points on the graph. Okay, to find an intercept, set the other variable equal to 0. So if you're finding the x-intercept, of course you set y equal to 0 and vice versa. Okay, to state an intercept, always write it as a point, coordinate, or ordered pair, as we talked about just a second ago. So always write it as such. X-intercepts are also called zeros, so you can see them be called zeros or roots. We're probably going to hear roots more often, but just be aware you could see zeros, could see roots. You might even see solutions sometimes. So those are all words to describe x-intercepts only. Okay, so VA stands for vertical asymptotes. So your vertical asymptotes are written in the form x equals a value. Set the denominator equal to 0, then solve to find vertical asymptotes. To find horizontal asymptotes, which are written in the form y equals some value, some number, you will look at the degrees or highest exponent on the variable of the given function. So you're going to look at the degrees of the numerator and you're going to look at the degrees of the denominator. So sometimes called f of x in the numerator and g of x in the denominator. So for the horizontal asymptote, if the degrees, remember we're talking about the degrees, if the degrees on the numerator is less than the degrees on the denominator, then y equals 0 is your horizontal asymptote. If the degrees in the numerator equals the degrees of the denominator, then y equals the leading coefficients of the given function will be your horizontal asymptote. And last but not least, if f of x is greater than g of x, then there's no horizontal asymptote, meaning if the numerator degrees is greater than the denominator degrees, there's no horizontal asymptote. More on this later. Stay tuned. Okay? All right, so when we graph, because that's a big thing we're going to be doing, once you get the features, of course you want to do something with it, graph it. Here's what you do. So you graph all the key features found, and then you plug in a few extra points where needed. So let's go ahead and hop to it. Okay, number 1. So of course you're going to find all these key features, and then we're going to see if we need to find any extra points, and then we're going to go ahead and start graphing. Okay, so the first thing, let me get all my stuff out of the way here. First thing you want to do to this equation is factor it if possible. So factor it if possible. So this is the, what did I call this before? Unfactored. I'm going to call this the unfactored version. Unfactored version, and then we want the factored version. So this is the unfactored version. Now let's look at the factored version. So of course you're probably looking at that denominator and you're saying x squared plus 6x plus 9. Oh yes, Miss Garcia, that can be factored because numbers that multiply to 9 but add to 6 are 3 and 3. So that would leave us with x plus 3 times the quantity x plus 3. So the quantity x plus 3 times the quantity x plus 3. Okay, so then you have your unfactored version and you have your factored version. You always want both. Okay, and I'm labeling these now. You'll see why in a minute. So I'm going to bubble both because you always want both. So there's our unfactored version. Here's our factored version. Okay, and remember, things will change a little. We'll talk about it when we get to number 2. But things will change a little when I go back to my original paper here. And remember how holes are where factors cancel. So do we have any holes here? Do we have any factors from the numerator and denominator that cancel? No, we don't have any matching factors. So some things are going to change a little bit when you have holes, and like I said, we'll talk about that when we get to number 2. Okay, so part A, roots. So remember, go back to this, sorry. Roots are your x-intercepts, okay? So to find an intercept, set the other variable equal to 0. So what does that mean? That means, so roots mean x-intercept, which means set y equal to 0 and solve. Okay, so it doesn't really matter which version you use. I typically use the factored version for this. Well, actually, in this case, it doesn't matter, but I will show you why it does in a minute. So we're going to use always the factored version. So that's why I'm saying FV here for factored version. So we're going to use the factored version for this always. So factored version, and then let me get my pen. So 0, n for y, 0 equals, and then we have 3 over the quantity x plus 3 times the quantity x plus 3. Okay, how do I solve? Well, 0 over 1, cross multiply. 0 times anything is 0. So is that going to happen every time I find an x-intercept? Every time I find an x-intercept, if I've got a situation where I have a fraction like this and I plug in 0 for y, plug in 0 for y here, I'm going to put the 0 over 1 and cross multiply. That's always going to get rid of what's in my denominator. What's in my denominator is going to turn to 0. So essentially for this, I can say that this is always going to be 0 equals the numerator, because this is always going to be 1. This left side is always going to be 0 over 1 to find the roots. So therefore, you're always going to have a situation where 0 equals the numerator is going to give you your roots. So just memorize from this point on that to find the roots, all you have to do is set the numerator equal to 0. In my opinion, easier, saves you a step. Okay, so in this case, when I set my numerator equal to 0, is that a true statement? No, 0 does not equal 3. That's because there are none roots. There are no roots for this graph. Okay, so I have no roots. Then let's talk about VA. So again, I'm referring back to this. For VA, it's an x equals form. Set the denominator equals to 0 and solve. So this is denominator equals 0. All right, so again, you will always want to use the factored version for VA. Okay, so set that denominator equal to 0. So 0 equals my denominator, each factor, x plus 3. There's no reason for me to set x plus 3 equal to 0 twice. I know I'm going to get the same answer twice. It's x equals negative 3. That's my VA. Okay, I don't have a VA at negative 3 and then another VA at negative 3. That's silly. There's just one at x equals negative 3. Okay, so there's my VA. Now for the HA, a little bit more complicated, right? So we need to look at our chart. Remember, we're looking at the degrees. If you want to look at the degrees, that means the highest exponent. You don't want to look at the factored version. So for this, we'll say unfactored version. So we're looking at the unfactored version whenever we do HAs every single time, unfactored version. So Let's look at the degrees of the numerator, the degrees of the denominator. I don't know if you remember this, but a constant, a number without a variable, has a degree of 0. So the degree in the numerator is 0, the degree in the denominator is 2. So which one's bigger, the numerator or the denominator? Okay, hopefully you would say that this is a situation where the numerator, the degrees of the numerator, is less than the degrees of the denominator. So we know we're using the degrees. And we know that the numerator, the degrees of the numerator is less than the denominator because the numerator, the degrees was 0 because there's no x. You can imagine that there's an x to the 0 there because, hello, what is anything to the 0 power? 1, and what's 3 times 1? Well, that's 3. So you can imagine x to the 0 there, so the degree would be 0. The degree there is 2, so therefore 0 is less than 2. That's a true statement. So what happens? Then you have a HA at y equals 0. I know this is a lot, but hopefully you'll start to get the hang of it. Okay, part D. Part D, we're looking for the y-intercept. So again, another intercept. So an intercept is where x equals 0 in this case because we set the other variable equal to 0. So if I set x equal to 0, actually in this one, it doesn't matter if you use the factored version or unfactored version. You could use factored version or unfactored version. Either way it'll work. It's kind of to each his own. I kind of flip back and forth, to be honest. So I'm going to do, you know what, I'm going to do the unfactored version. Y equals, and you know what, better yet, let's use some proper notation here. I'm really computing f of 0, aren't I? I'm plugging in 0 where I see x. So f of 0 equals 3 over 0 squared plus 6 times 0 plus 9. Now again, if I used the factored version, would I get the same answer? I hope so. We'll go back and check. So this is f of 0 equals, plugging in 0 where I see x, remember? I have 3 over, oh, I love using the unfactored version when this happens. 0 here, 0 here, right? Anything times 0, 0, and then 9. So 3 over 9, so f of 0 equals 1/3, agreed? So here you would put 0, comma, 1/3. Yes? Everybody see that? Okay, so if I plugged in 0 here into the factored version, would I get the same thing? So I'd have 3 over 0 plus 3, 0 plus 3, so that'd be 3 times 3, which would be 9, 3/9, which would be 1/3. So yeah, either way, you're going to get the same thing. Okay, now for the fun part, graphing. Yay, so remember, find all your key parts, then start graphing. So I have no roots. I have a vertical asymptote at -3. X equals -3. So 1, 2, 3. Here's my vertical asymptote. All right. I have a horizontal asymptote at y equals 0. So make it distinguished. Draw some dark lines there on top of the y-axis, x-axis for the y equals 0 line, okay? And then I have a y-intercept at 0, comma 1/3. So I'm gonna make these ticks a little more spread, just so I can see what a third looks like. Okay, so about there. Okay, so think about this, y'all. This curve here is going to be pulled close to the asymptote. Okay, the asymptote acts like a magnet. So there goes your curve being pulled close to this asymptote, being pulled close to this asymptote. So here's my curve here. Can I have a curve here? No way, that would make a non-function. Now I probably have a curve either here or here. How do I know? Do I know for sure it's here? Do I know for sure it's here? No, I don't. I don't have any other information to give me that information. So that's where this last part comes into play. Plug in a few extra points where needed, right? So I need to know what's happening on this side of my graph. Well, what's the x value? -1, -2, -3. Let's find out what's happening. Extra point. where x is -4. Let's call this f of x. Ooh, I like that. Okay, so -4. So I'm going to come in here. Again, does it matter which version you use? No, I typically kind of flip back and forth, to be honest. I do. So, ooh, I don't want to plug in -4 there. I'm going to do it on this version. So that would give me 3 over -4 plus 3, and then -4 plus 3. So that's going to give me 3 over -1 times -1, which is really 3 over 1, which is 3. So my extra point is going to be -4, 1, 2, 3. So that worked out nicely because it fit on my graph. So anytime I have an extra point, I'm going to label it -4, 3, because that's the point I found. So now I know my curve is in this, quote unquote, if you're looking at this as your new origin, like my second quadrant here and not the third quadrant here. So I know that my curve is going to be here, and I know that it's going to hug the asymptotes. The asymptotes are going to pull it in. And of course, we're not going to cross this asymptote. If I want to stretch this out, since I know it's over here now, I could stretch this out just so I show that this curve is never going to cross, never going to touch. Same going up here. That curve is never going to cross, never going to touch. Okay, another example, number 2. All right, so first thing you want to do is factor. So we're going to factor this guy. This is the unfactored version. Let's factor. We would get y equals numbers that multiply to 21 but add to 10. So that's going to be 7 and 3. X plus 7, x plus 3. Over x plus 7, x plus 5. Okay, so what do we have here? We have a situation where factors cancel. Remember, that creates a whole. So what do we say here? We say y equals x plus 3 over x plus 5. This is actually our new equation. Okay, we are not going to ever go back. So I'm going to put a note here. Don't go back to original when there are holes. So when there are holes, we're not going to go back to the original to plug any of this information in. The only time we would go back to the original is except to plug in y equals of calc. That would be the only situation. If you want to plug this in the y equals of calc to graph, to check your graph, then of course you would go back to this original one, not this, because it wouldn't show the hole because you've gotten rid of it. So that's the only way. Otherwise, when you're computing all your math, you will just stick with this guy. So this is technically the unfactored version and the factored version all in one, because technically it's kind of unfactored and it's factored. It can't factor any further. So it's kind of strange sometimes when holes happen like that. So what we're going to put off to the side too is we're going to say hole at x equals -7, right? So you set that factor equal to 0 and solve, and that would tell you where your hole is. But here's the deal. Yeah, I have a hole at -7, but that's an ordered pair. It's not a line. So we're not going to keep it like this. We're going to find the ordered pair. So we're going to plug in -7 here and here. So we're going to compute f of -7. So f of -7 would be -7 plus 3 over -7 plus 5. So f of -7 would equal, that's going to give me -4, that's going to give me -2. -4 divided by -2 is going to give me +2. So I'm going to have a hole at really -7, 2. So that's really what you want to keep into consideration here, is there's a hole at the point -7, 2. A lot of work to be done there, I know. Okay, remember roots. Roots is where you're going to set the numerator equal to 0. We went through that whole spiel last time. This is numerator equal to 0. This is denominator equal to 0. This is degrees. Just going to kind of write it all out so I can get rid of my pink pen here. This is looking at the degrees. You're going to do this every single time. And this is when x equals 0, my y-intercept. Okay, so these stay true every single time. So now let's go to town and go to work. So my numerator equal to 0. Remember, I don't go back to the original when they're whole. So this is all I'm looking at. So numerator equals 0. So 0 equals x plus 3. Well, that's easy. X equals negative 3. But I don't leave it like that. I write it as an ordered pair. It's an x-intercept. Okay. Now here, denominator equal to 0. X plus 5 equals 0. So x equals negative 5. Okay, for the VA, I do keep it, it is a line. I do keep it as such. X equals negative 5. Okay, my degrees. So my degree in my numerator is 1. The exponent on x is 1. The exponent on x is 1. 1 equals 1. Okay, so my numerator equals my denominator. What does that mean? Go back to your handy dandy chart here. Right? When they equal each other, then you take the leading coefficients. So what are my leading coefficients? My coefficient here is 1, and my coefficient here is 1. 1 over 1 is 1. So y equals 1 is my HA. Okay, so for my y-intercept, x equals 0. So really, I'm finding f of 0. So 0 plus 3 over 0 plus 5. So f of 0 equals 3/5. So 0, 3/5. Okay, so now let's start graphing. So I have a root. I actually have an x-intercept at negative 3, 0. I have a vertical asymptote at negative 5. X equals negative 5. Okay, and I have an HA at y equals 1. Whoops. Got a little crooked there. That'll bother me a little. Okay, what else do I have? So I have my HA, have my root, VA, y-intercept, 0, 3/5. Maybe there. That makes sense because, so in this quote-unquote like quadrant, if you want to call it, here's my curve. So therefore, since my curve is hugging my asymptotes, remember my asymptotes are pulling that curve closer to it. I know I can't have a piece up here because that would create a non-function. I know I'm probably going to have a piece either here or here. How do I know where it's at? You guessed it, that extra point. So let's find that extra point. So remember, I want the x value of -1, -2, -3, -4, -5, -6. So x, f of x, or y. So I want -6. So if I plug in -6, so -6 plus 3 over -6 plus 5, so that gives me, that's an arrow, -3 over -1, so 3. So -6, +1, 2, 3. So that means we're in this quote-unquote quadrant here, this part of the box here. So that means I can't have a piece down here because that would make a non-function. So that's all there is to it.